In this video, I'm going to do some simple demonstrations of a mechanical resonance using this weight here, which is just a wrench, and it's tied to a daisy chain of rubber bands. If I hang the weight like that and then kind of kick it, it bounces at some frequency. That's its natural frequency of vibration, which is that frequency. And then the vibrations gradually die out because damping is converting its mechanical energy into heat. So to show you resonance, I'm going to drive the system by providing a driving force at the top of that rubber band chain. And I'm going to do it at the same frequency. To refresh my memory, I'm going to get that locked in my head as a musical tempo again. And now I'm just going to move my hand a little bit, about 1 or 2 centimeters at that frequency. So like this. Still only moving my hand about 1 or 2 centimeters, but the response from the wrench builds up and builds up. That depended critically on the fact that I was driving it at its natural resonant frequency. As an example of what happens when I'm not at the resonant frequency, I can do something like this. So now I'm shaking my hand really hard. You would think I'm making a lot of effort that would produce some big effect. Not much is happening. The wrench is kind of twisting there in the air, just waving in the breeze, but I'm not getting much of a vertical response. None that I can really see for sure at all. And then I can also do the opposite extreme, which is a frequency much lower than the resonant frequency. So for that, I'll go like this. Calm down the wrench. I'll go like this. Up and down. This one's about as exciting as watching paint dry. And I think you can see that all that's happening is, at any given time, the wrench is approximately in equilibrium. The rubber band chain keeps the same length the whole time, and therefore the wrench just matches what my hand does. So there's a response. It's not zero. It's pretty easily observable, but it's not any bigger than just what my hand is doing at the other end of the rubber band. So let's represent the results of that experiment on a graph. On the x-axis, I'm going to put the frequency omega, which is 2 pi times the frequency f. Usually people refer to them both as frequency. You have to just know from context which is which. And then on the vertical axis, I'm going to put the energy of the steady state response. This is just sort of conventional. We didn't actually measure any energies in this experiment, but one way to do that, if we wanted to do a quantitative real experiment, is that we could have measured the amplitudes and squared them, because in general the energy of an oscillator is proportional to the square of the amplitude, at least when the oscillations aren't too big. So originally I drove it at a frequency that was like the Goldilocks and the Three Bears frequency. It wasn't too high, it wasn't too low, it was just right. And I got a big response. So in fact, I never really reached a steady state. I kind of chickened out and stopped because the wrench was about to hit me in the face. But we'll say that there's some very big response when I keep on going at the resonant frequency. So that would be similar to pushing a kid on a playground swing. You keep on pushing, eventually they go as high as they're going to go. Then the next one that I did was the very high frequency. At the very high frequency, I got almost no detectable response. It was basically zero as far as I could measure. And so what happens actually is the high energy response approaches zero, the high frequency response approaches zero asymptotically. At low frequencies, I did get a response. It responded by moving just as much as my hand was moving. So it wasn't approaching zero or anything, but it was quite small. So that would be a point like that. And so now if I smooth in the whole curve, it's going to look something like this. which is curve with a classic mathematical shape. Sometimes people call it a Lorentzian. We haven't said anything yet about why resonance occurs, why these systems like to be driven at their natural frequency. To try to show that, I've set up this pendulum bob, which is hanging from a ruler stuck into that paint can up on the shelf there. And I'm going to drive it with this piece of PVC pipes by hitting it. So it's not the idealized kind of sinusoidal driving force, like F being like sine of t or something, that we were talking about before, but it's a nice, easy way to show a nice interpretation. So here's the natural frequency of this pendulum. So it's that. And now when I drive it at that frequency, it responds a lot. The really nice observation that helps to understand what's going on is to drive it at exactly twice its resonant frequency. So I'm going to do that by first committing to memory the resonant frequency of this thing. So that's that. So now I have to double that frequency. That's like taking musical quarter notes and turning them into eighth notes. So it's like tunk, 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 tunk. Now I'm going to hit it at that frequency, which is twice as high as the resonant frequency. Tunk, tunk, tunk. I think you can see that each time I hit it, I get it going, but then on the way back, all I'm accomplishing is to stop it. So the response never builds up at all. What's happening here is that when I hit it at resonance, each time I hit it, I'm hitting it while it's moving away from me. So the force and the motion are in the same direction, and I do positive work. But when I'm off resonant frequency, the phase relationship between the driving force and the motion gets messed up. And in the example I did, exactly half the time I was doing negative work because the force and the motion were in opposite directions. So on the average, I was not putting any energy into the vibrations. So in the example of the playground swing, where mommy pushes you right at the resonant frequency, you get a big response, but not infinitely big. It always seemed like, to me, I would usually get about as high as about that on the swings, no matter how hard I tried to pump or how hard my mother pushed me when I was littler. Never got any higher. You could ask, what would determine that? Well, it depends on the amount of friction in the system. So, for instance, say you have a kid who grew up in a playground that has, the ghetto swing set that has a lot of friction, and that's this response. But then they go to the rich kids' playground in another part of town where there's less friction. How would the curve look different? I think most people would be able to predict pretty confidently that at resonance, you would get a bigger steady state response because there's less friction sucking energy out of the system and dissipating into heat and sound. The other interesting thing is that not only does it make it a higher peak, but it also makes the curve narrower. Exaggerating a little bit here. Something like that. So in our original black curve, the full width at half maximum, which is like you measure halfway down from the peak, and it's that far across, was that. Whereas with the new red curve, the width is smaller. And we could ask, how do you quantify this sort of thing? In order to quantify it, you need to define some numerical measure of how much friction there is in the system. So for this purpose, we define this quantity called Q, or the quality factor, which is the number of oscillations that are required before the vibrations die out so far that their energy goes down by this factor. It's kind of a funny looking definition, but defining it this way makes some of the other formulas come out simple. And this happens to equal about 1 over 535. And if we wanted to measure that in an experiment, the energy of the vibrations is approximately proportional to the square of the amplitude. That's basically just because the energy is an even function of the amplitude. You can't have negative energy if the amplitude's negative. That would just represent a phase flip. And so any smooth function that is an even function is going to look like something squared. if you're talking about small values of the independent variable. So since this definition refers to the energy, if we wanted to measure the amplitude, which is usually easier, we would have the amplitude going like the square root of the energy. And that means in order to apply this definition directly, we want the amplitude to go down to 1 over the square root of 535, which is about 23. So let's measure the Q of the wrench on the end of the rubber band chain. I needed a nice clear background, so I asked my Rhino to help me with that. So I think I've lined this up so that the top of the wrench is just lined up with my Rhino's shoulder. It's a good reference point. I'm going to pull the wrench down 23 centimeters, and measuring with this ruler. So now the initial amplitude will be 23 centimeters from center to bottom. And then I'm going to count how many oscillations it takes until the amplitude goes down to 1 centimeter. 1, 2, 3, 4, 5. I think it was actually around 4 oscillations that the amplitude got down to about 1 centimeter. It was a little bit messy. So that Q of that oscillator is about 4. So returning to our graph, if we take that full width at half maximum and call that delta omega, then that width goes down when we increase Q. This red curve is for a higher Q. And more quantitatively, that relationship looks like this. So the width depends on the resonant frequency divided by the Q. If we reduce the amount of friction and make Q bigger, not only does the peak rise, but the width also gets smaller. To understand the reason for that relationship between the Q and the width of the resonance peak, let's go back to our 2 oscillators, one of which had a big Q and one of which had a small Q. This one has a big Q. If I started oscillating, if that was, let's say, 23 centimeters of amplitude, I think you can see it's a lot more than 4 oscillations before it gets down to 1 centimeter. It's barely even gone down at all. I measured this one's Q earlier today, and it was something like 20. With something that's got a high Q like this, if I give it a little tap and then wait a long time, it remembers when I tapped it, and it knows when it wants to be hit. It matters whether I hit it at the right time, when it's going away from me, because that'll do positive work, or if I hit it at the wrong time, like that, then I'm kind of stopping it and doing negative work. So if I'm building up energy gradually over time, this thing wants to be driven right at the resonant frequency. Otherwise, the driving force and the motion sort of gradually get out of phase, and it remembers what phase it wants, and I start doing negative work. On the other hand, if I do that with this oscillator that has a low Q, I can kick it, and if I wait, its Q is about 4. After 4 oscillations, it doesn't remember what it's doing. It's basically stopped. It doesn't care when I hit it again. It's lost its memory of what its phase used to be. That's why this oscillator is going to be relatively insensitive to what frequency you drive it at, and you'll still have a fairly big response even off resonance. As an even more extreme example, I could take this heavy weight, and if I push it to the right and then wait a while, it doesn't care when I push it again now. I could push it now or at some other random time. Because there's so much friction in the system, it just immediately loses its memory of what it was previously doing. Now I'm going to demonstrate the phase relationship between the driving force and the response. I've got this heavy paint can hanging from a tree in my backyard, and a couple of rubber band chains here so I can provide a small driving force. Here's the natural frequency of the can. So that to that is one period. Now I'm going to drive it at that frequency, so it'll be at resonance. The force from the rubber bands is very small, but because we're near resonance, we're getting a lot of response. And I think you can see that the times when I'm applying the most force are the times when it's sweeping through the bottom of its arc. So now, 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 now. So what that means is that I'm doing the maximum amount of work. When it's moving to the left, I'm applying a force to the left, and that does as much positive work as I can do. When it's moving to the right, I apply a force to the right. And so in that condition, when I'm at the resonant frequency, the displacement is zero at the time when the force is at its maximum. So the force and the displacement are 90 degrees out of phase. Okay, now I'm going to show you the extreme case where the driving frequency is much less than the resonant frequency. If I do that with the rubber bands, it's actually pretty hard to see. I can pull a little bit to the left, I can pull a little bit to the right. I think you can probably just barely see that it's moving at all. So to make that easier to see, I'm just going to use my pinkies to apply a little more force. With zero force, I'm at zero displacement. Now if I push with a little bit of force to the right, there's a little bit of displacement. Maximum force to the right gives the maximum displacement. Now I'm easing up on the force, the displacement comes back down to zero, zero force at zero displacement, and so on the left-hand side. So essentially the system's always in static equilibrium because the frequency is so low. And for that reason, the displacement is in phase with the driving force in this condition. Okay, now I'm going to demonstrate the extreme where the driving frequency is much greater than the resonant frequency. If I try to do that with the rubber bands, the response is so small that it's basically impossible to see. I see the can wiggle a little bit, but it's not actually moving the rope. So in order to understand why that would happen, think about the constant acceleration equation, 1/2 at squared. This is not really constant acceleration, but pretend it is. So if I give this can a time t to respond to that force, the distance it's going to move is going to go like 1/2 at squared. It's proportional to t squared. So when the frequency is very high, that time is very short, and it can't travel far enough in that time before I change the force and go the opposite way. So at high frequencies, we expect the response to go like 1 over the frequency squared, which means it's too small to see with that small force. So to make that effect big enough to see, I'm going to use a bigger force supplied by these two pieces of bungee cord. And so now if I drive it at a very high frequency, because the force is so big, you get enough response to see. And I think you can see the phase relationship now. When my hands go to the left, the can is to the right. When my hands go to the right, the can is to the left. They're exactly opposing each other in phase. Let's use a graph to summarize our observations with the paint can. On this axis, I'm going to put the phase shift, and we saw it vary from 0 degrees to 180 degrees. On this axis, I'm going to have the frequency, and we'll say that the resonant frequency is right there. So in the limit of very low frequencies, the displacement was in phase with the force because the system was always approximating equilibrium. So we'll put a dot there. When we were at resonance, the force was doing the maximum amount of work, meaning that the force was at its maximum right when the can was swinging through the bottom at a displacement of 0. So that's a 90-degree phase difference. And then in the limit of high frequencies, we observed that the can and the force were out of phase by 180 degrees. And if we smooth in a curve through these points, what it actually looks like is something like that. For the rest of this video, I'm going to present a mathematical derivation of the facts that we've seen so far. Some of those facts we've seen purely empirically, others we've seen with a little bit of mathematical justification, but now we're going to get into the actual mathematical details. And if you don't want to see all the derivations, then you could simply stop watching the video at this point. So we've been dealing with all of these different functions, the force, the position of the paint can, and so on. They're all sine waves of some kind, and they have different amplitudes and they have different phases. So here are a bunch of examples written on little scraps of paper of different sinusoidal functions. And we're going to think about how to just classify these as if we had a bunch of butterflies and we're going to put them in our butterfly collection. One thing you could say is that there's this one, which is a trivial example, but it's obviously important, the zero function. So we'll put that right in the middle there. And then say we have the sine. Well, that's our kind of normal example of what a sine wave is. Let's put it next to that right there. The cosine differs from the sine by 90 degrees in phase. So it's kind of arbitrary how we want to arrange these stamps in our stamp collection, but let's just say we're going to do this, which would kind of make sense, because then that would be a 90-degree angle right there. If we're going to continue with this system, it seems like we should clearly have minus the cosine over here. That makes sense because if the cosine is 90 degrees in phase ahead of the sine, well then the minus the cosine is 90 degrees in phase behind the sine in turn. An example like 2 sine is going to have to go there, right? Because there we've got 0 times the sine, 1 times the sine, 2 times the sine. And then it's pretty clear that an example like that should go over there. So in this way, we can kind of cover the whole plane with dots, and each dot represents a different sine wave. Here's the system you get when you do that, and now nice things start to happen. Let's take one of our examples like that. It behaves like some familiar mathematical systems that we've seen before. Let's say that we think of 2 times the sine function as an arrow going from there to there. And then the cosine function, we think of that as an arrow going from there to there. We're adding these two functions. Well, we're used to adding arrows like that. We take this arrow and then we put it tip to tail with this arrow, and we get this one. So that's exactly how we're used to things behaving when we do vectors and also the complex numbers. Another nice thing is, suppose we wanted to find the amplitude of this function. That's kind of hard, actually, if you think of it just as a trig problem. You have to use trig identities that you've probably forgotten since you took your trig final. But we can just associate the amplitude of that with the distance that this point lies from the origin. So it's 1, 2 over and 1 up. So that distance from there to there is the square root of 5 by the Pythagorean theorem. And in fact, that's the amplitude of that sinusoidal wave, is the square root of 5. So that was a nice way of visualizing some trigonometry and figuring out shortcuts for finding things in trigonometry. Let's do some calculus now. We've got this function sine omega t. Let's say that omega is 1. Then the derivative of sine of t with respect to t would be cosine of t, which would be this function right there. The derivative of the cosine is minus the sine, and so on. So every time we do a derivative, we go 90 degrees around in this plane. And that's just a way of visualizing something we already knew, which is that when you take the derivative of a sinusoidal function, you get a phase shift of 90 degrees. We could also do cases where omega is not 1. So for instance, let's now say that omega is 2. Sine of 2t, then we take the derivative of that. The chain rule is going to give us another factor of 2 out in front now. So it's going to be 2 cosine omega t. That sends that point to that point. So now we do a 90-degree rotation, and we also scale up the function by omega, which in this case was 2. If we now take the derivative of 2 cosine 2t, we actually get minus 4 sine 2t, which is over here. So every time we take a derivative, we just turn 90 degrees and scale up by the factor omega. It also works for derivatives, also works for integrals. You go the opposite way and you scale down by omega. Now it turns out to be nice if we associate this plane with the plane of complex numbers. That's not going to be immediately obvious why, but bear with me for a moment and I'll try to show you why that would be. So obviously this would be the complex number 0. 0, you might say, well, that's a real number. Well, every real number is also a complex number. Just like every rectangle is, every square is also a rectangle, or every poodle is also a dog. So there's 0 as a complex number. Then this we're going to call 1. So this part of the plane becomes associated with the positive real numbers. 2, 3, minus 1, minus 2, minus 3. Then this point up here we associate with the complex number I, which is one of the square roots of minus 1. The other square root of minus 1 is down here. That's minus I. And then an example like this would be 2 plus I. So then in these terms, the quantity we were talking about before, which here is the square root of 5, that's called the magnitude of this complex number. And then there's also an angle you can talk about. That angle is called the argument of the complex number, and that's how we represent phases in this system. You don't have to make this connection. You don't have to label these as the complex numbers. Sometimes in freshman electricity and magnetism classes, they'll refer to these things as phasors rather than complex numbers. It always makes me think of Star Trek. But in real life, by the time people are professional scientists and engineers, they really do think of these as complex numbers. And I'll show you a simple way of seeing why that's a natural thing to do. If we take I to the first power, we get I. So that's right there. Then I to the second power, well, I is sort of defined as the square root of minus 1, so that's minus 1. So now we're over here. I cubed, well, here you would have I squared times I, so minus 1 times I. So that's down here. And then I to the fourth, it's going to be that times I. If you work that out, that comes out to be 1. So what you can see is happening here is each time you multiply by I, you're going around in the complex plane by 90 degrees. And that's so similar to the ideas about phase and derivatives that we were talking about before, that it really makes us want to use these complex number labels for these points. And that's all they are. They're labels. They're just ways of assigning a certain thing to a certain thing. So if I say, you know, Donald Trump is like chocolate and Joe Biden is like vanilla, then those are just labels. They don't really mean anything, but they could be useful labels. So that may have all seemed hard and scary, but maybe also a little bit fun, I hope. And here's the payoff. It makes our treatment of resonance and oscillations really, really simple. So let's say we have our basic example of a box sitting there with some mass m, and it's connected to the wall over here by a spring with a certain spring constant k. And we're also going to model the friction on this box by saying that the force of friction equals minus b times the velocity of the box. So b is some constant, and so if v is positive, then friction is to the left and is trying to slow down the box, so we get a negative number here. And if v is negative, of course, the frictional force comes out positive, meaning that as the box is going to the left, there's a positive frictional force, again, trying to slow it down. This is not necessarily how friction really truly behaves for this box sliding on a solid surface. Most likely the force of friction actually doesn't increase with velocity. That's the model of friction they taught you in physics, in your first semester of physics. But this model turns out to have nicer mathematical properties, so we use it, and once we have made the model, it gives us a lot of guidance even in cases where this exact model of friction is not true. So if we write down Newton's second law for this system, we have Newton's second law like that, and this F is the total force. It's the sum of all the forces acting on the box. So we have a force from the spring, which is that. We call that Hooke's law. And we also have the force of friction, like that. And we could also have a driving force. So in fact, here I'll call this F total, because I want to reserve the symbol F for my driving force. This thing, x is the position, v is the same thing as the derivative of x, and then this acceleration is the second derivative of x. So if I just rearrange this equation a little bit, I get something that has this nice simple form. So it's kind of pretty. It's got the second derivative, the first derivative, and the zeroth derivative, or the original function itself. Each one multiplied by some constant, which is a positive real number, and then that just is what is going to equal the driving force, which is a function of time. So now we're going to play this trick with our complex numbers. So we're going to associate this driving force, which is a function of time, with some complex number, and we're going to call that f with a tilde on the top. And then on the other side of the equation, we're going to say that the position, which is a function of time, is some sinusoidal function. We're going to associate that with a complex number a. When we differentiate a sine wave, remember we rotate 90 degrees and we also multiply by the frequency. So that means we're multiplying by I omega. So the complex number that represents the function x prime is going to be I omega times a. And then when we take a second derivative, there's another factor of I omega. So I omega times I omega is going to give us minus omega squared. And we get that. So what's really nice about this is that we've taken this, which is about functions in calculus, and we made it into just an equation relating some numbers. So that's a big win. It takes our calculus problem and turns it into an algebra problem. So then this was some scary differential equation. I don't know, how would you have guessed what the solutions to that would look like? But this is not some difficult differential equation. This is just algebra. So we want to predict the response of the object to this driving force. That just means we solve for that number, a. So if we factor out the a, we're going to get a bunch of stuff times a on this side, and then divide by that stuff to get a, and we end up with this. And that's it. Every fact that we saw about the resonant behavior of a mechanical resonance, how much it responds at different frequencies, its phase response, all of that is in that equation, and we didn't have to do any real calculus or differential equations to find the result. So that's super nice. One thing that we can do just to verify that this makes sense quickly is we would kind of expect that when the frequency is close to the resonant frequency, close to the natural frequency, we would get a big response. So let's see what happens then. We already know from more elementary treatment of the harmonic oscillator that the natural frequency, which we'll call omega naught, is going to equal the square root of k over m. So let's see what happens when we plug that in here. Then in the denominator, we're going to get omega squared, if we plug in omega equals omega naught, so that's going to be k over m. So I think you can see something nice is going to happen here. Well, this term is minus k, this term is k, those two terms are just going to cancel. And we get a big result because the denominator is pretty small. We made the entire real part of that denominator go to 0, and all that's left is this imaginary part. In fact, if we take the case where there is no friction, the case where there is no friction would be the case where b equals 0. Well, then the amplitude would blow up to infinity, and that kind of makes sense. If you drive an oscillator at resonance and there's no friction, there's no mechanism for dumping energy out into heat, so it'll keep on absorbing the energy you're putting in indefinitely, and it'll actually never reach its steady state. This is the steady state response that we've been describing here. If we want to know the amplitude of the steady state response, we just have to take the magnitude of this complex number a. When you have a complex number divided by a complex number, the magnitudes just divide. And then the magnitude of this thing is going to be its distance from the origin in the complex plane. So if I sketch that, the real part of it is going to be k minus omega squared m. The imaginary part is going to be omega b. And so we have a point over here. And its magnitude is the distance from the origin to there. So it's like the Pythagorean theorem with that as one side of the triangle and omega b as the other side of the triangle. So we get that. And this is the function that we've been graphing that looks sort of like this. That's the Lorentzian function. When I was doing my stuff with the paint can, I argued that the response at very high frequencies should go like 1 over omega squared. We can actually see that here. So when omega is very big, then this term gets very big compared to this one, so the k term is negligible. So I'll cover that up with my pen. Also, when omega is very big, this term, which goes like omega to the fourth, is very big compared to the omega squared term, so we can forget about that term as well. And so we essentially just have that, which simplifies to that. Because remember, we had this square root on the outside. So just like I argued before, in the limit of high frequencies, we do get a very small response that tails off like 1 over omega squared. At 0 frequency, it's also easy to see that we do get a small but finite response. If omega is 0, that term goes away, that term goes away. We just get some number, which is f over k. And again, that makes sense because at very low frequencies, the force is just k times the displacement because it's in static equilibrium approximately. So this is just kx over k, so we get x. That's just the displacement, which is the same thing as the amplitude we're talking about. And finally, let's use our result to explain those facts about phase, most of which I only kind of showed as observations or gave hand-waving arguments before. So if you recall with the paint can, for this phase angle at low frequencies, I gave an actual argument that the phase angle should be 0 because it's approximately in static equilibrium when you're at very low frequencies. At resonance, I just argued that you would be doing a lot of work on the paint can, so that would help you achieve resonance, but I didn't prove that this was exactly a 90-degree phase angle under those conditions. And then at very high frequencies, I just showed you the experiment, but I didn't explain why the force and the displacement would be exactly 180 degrees out of phase in that limit. Well, we now can show that mathematically. So here's our result for the response. This is A for amplitude, but this is a complex number A, so it encodes both the information about the amplitude of the sine wave and its phase. So if we want to visualize this A in the complex plane like that, let's call these points 1, 2, and 3. So at very low frequencies, if omega goes to 0, these two terms go away, and we just get the force divided by the spring constant. It's in static equilibrium, as we saw with the paint can. You just don't get very much displacement when all you do is provide a small force. So that's going to be a small number, and it's going to be positive and real because this is the force which is divided by this positive k. So if we're taking the force to be, let's say, a sine wave, then dividing that by a positive real number will still give a positive real number which represents a sine, not a cosine or minus the sine or something like that. So we're going to get a number that's fairly small and positive real. Then when we drive it at resonance, we start to get cancellation between this positive real term and this negative real term in the denominator. And that cancellation of that real part is perfect at resonance, or at the natural frequency. So those two terms go away. And so we now are taking our F tilde, which is a real number in our example, because we're saying the driving force is a sine wave. We're dividing by an imaginary number, and that imaginary number is fairly small if the friction is small, so B is small. So we're dividing a real number by a small imaginary number. What that gives us is a big negative imaginary number. So there's our 90-degree phase shift. And finally, in the limit of very high frequencies, this term dominates. This one and this one become negligible by comparison. So we're taking our real F tilde, dividing it by a negative real number, and we get a negative real number, and it's going to be a small negative real number. As omega gets big, it's going to get small, like 1 over omega squared. So we're going to get something like that. So now we see the phase angles here from this formula. And the fact that this is at an angle of minus 90 degrees in the complex plane is just telling us that that's a question of how we lay out our plus and minus signs on here. So I hope that was kind of a satisfying conclusion to this whole thing. It may have been a little bit scary to see it with the complex numbers, but I think the gain in the simplicity of the treatment is so great that it's worth seeing. Thanks for watching.